Okay, we've got a hard problem here. I don't know if this will be a math minute, math 10 minute, whatever. All right, so this problem comes from a physics textbook. The idea is we have some water tank. This water tank has some diameter. So imagine it's a cylindrical water tank, and its height is twice the diameter. Okay? Now, that's all nice and well and good. The problem comes from the fact that to fill up this water tank, we are going to shoot water out of a cannon into this water tank. And the distance away that this cannon is 6 times the diameter of the water tank for whatever reason. And this cannon is angled at 45 degrees. Now, the question is, what does the initial velocity of our water need to be such that it enters into the water tank? Now, there's going to be a range of velocities here. If it's too small, it won't make it over the front lip of the water tank, and if our velocity is too big, it will overshoot the water tank. So there's some range of velocities such that it goes just over that front lip or comes just inside that back lip. So what are these range of velocities? And we want to find them in terms of the diameter of this water tank and the constant g, which is of course the acceleration due to gravity. Okay, so how can we find this? Well, one thing we need to think about is that there are 2 components to this initial velocity. There's a horizontal component, which I'm going to call initial velocity x, and there's going to be a vertical component, which I'm going to call initial velocity y. Both of these are going to be equal to each other and to the initial velocity divided by the square root of 2. Hopefully, if you remember your 45, 45, 90 triangles or sine and cosine of 45 degrees, you believe that that's true. Okay. Now, this is important because we need to break down this motion of the water into its horizontal motion and its vertical motion. And we're going to set this up with a little bit of some equations. The idea is when our water travels 6d, so when it travels the distance from the foot of the cannon to the foot of the water tank, we need its height to be something above 2d. And then similarly, if we think about the horizontal movement after traveling 7d, which is the 6 diameter plus the diameter of the water tank, we need to make sure that the height is less than 2d, or the vertical distance is less than 2d. Okay, so let's think about this. Our horizontal movement has no acceleration. We're going to ignore air resistance for this, so we can sort of say the change in x is just going to be this initial velocity times time, and we'll set this point to be 0, 0. So we know the change in x is just going to be the initial velocity in the x direction times time. Because we're ignoring air resistance, this velocity doesn't change. And in fact, we can figure out like how long will it take to go 6d. Well, we just divide both sides by that initial velocity in the x direction. And if we substitute this in and do a little algebra, we can get an expression in just the initial velocity itself. So this will be 6 times the square root of 2d all over the initial velocity. So that's the time. This is how many seconds it's going to take for the water to travel from the cannon to that first lip of the water. Similarly, we can think the change in y is going to be the acceleration, 1/2 the acceleration. I'm going to keep g positive. So we're going to consider up to be a positive direction and down to be negative. So the acceleration due to gravity will be negative. And then we have our initial velocity in the y times time. And because we're starting at 0, 0, we don't have anything there. Now, we need this to be greater than, if we're considering this first case, this needs to be greater than 2d. Okay, so when using the time it takes the water to travel 6d, we need this function that tells us the height, the delta y, to be greater than 2d. So I'm going to take this time and I'm going to plug it into this inequality, and we'll get our lower bound for the initial velocity. And because we're keeping things in terms of g and d, I'm not going to plug in that constant. We're just going to keep going. It's going to get a little bit messy because we have 6 times the square root of 2d all over initial velocity squared. I'm again going to substitute this expression for the initial velocity in y. 6 times the square root of 2d all over initial velocity. And instead of inequality, we'll actually do the inequality because we want this to be greater than 2d. Okay, now we got to do some algebra and see what happens. We have this 2d is greater than negative 1/2 g. 6 squared is 36. Square root of 2 squared is 2, so that's 72d squared all over initial velocity squared. And then looking over here, we have some square roots of 2 that cancel, some initial velocities that cancel. So that's actually kind of nice. We have 6d. If we subtract 6d from both sides, we get negative 4d. We'll just keep writing this out. 72d squared all over VO squared. If we multiply both sides by negative 2, we'll get 8d. And we got to change the sign. And then we have g 72d squared all over VO squared. Again, we're trying to find a bound for initial velocity. So here I'll multiply both sides by the initial velocity squared and divide both sides by 8d. And this will get us pretty close. So we have g times 72d squared all over 8d. This allows us to cancel a little bit. I'm going to keep going over here. Velocity squared. 72 divided by 8 is a nice round number. We have 9g, and then d squared divided by d is just d. So our lower bound for the initial velocity is actually going to be 3 times the square root of that constant g and the diameter of the water tank. Okay, so we're basically halfway done. Now we need to think about what happens when the change in x is 7d. So when the water comes to this side of the water tank, we need the height to be less than 2d. So again, we saw what is the time that happens. You can see it's pretty much going to be the same idea. I just need to substitute this where I substituted this. So I can maybe simplify things. We need our height to be less than 2d this time. So we don't really get away with a whole lot of simplification right away, but instead of doing 6 times the square root of 2 squared, we're doing 7 times the square root of 2 squared, so that's 49 times 2, which is 98d squared all over VO squared. And then over here, we'll get some things that cancel, but we'll be left with 7d. I hope that's right. When we subtract 7d from both sides and multiply both sides by negative 2, so if I subtract 7d from both sides, I get negative 5, so I'll get 10d is less than 98d squared, g 98d squared over VO squared. If I multiply both sides by the initial velocity squared and divide both sides by 10d, I'm going to get initial velocity squared is going to be less than 9.8 times gd, which is good. So if I think about like just comparing this, we had initial velocity squared is greater than 9 times gd, and here we have initial velocity squared is less than 9.8 gd. So we're pretty much done. We just need to take the square root of both sides. I get the initial velocity is less than something like 3.13 times the square root of gd. Let me grab my trusty TI 84 CE edition. I'm sorry, TI 84 plus CE. The square root of 9.8 is, in fact, 3.13 and change. So the range of velocities, the final answer I'm going to say, is that our initial velocity needs to be greater than 3 times the square root of that constant g times the diameter of the water tank, and less than 3.13. So threading a fine needle here, these are the velocities we can choose based on the diameter and the constraints given in the problem.